In the earlier class, we have discussed about the thermal oxidation, which is one of the most important process steps in the process engineering of silicon or in any other device technology. So, today we shall discuss about the kinetics of thermal oxidation, and you can find that in this view graph that this is the semiconductor piece of sample, let it be silicon, and the oxide has been formed at one of its end through the oxidants. That means, we have assumed that a silicon sample in contact with the oxidizing species. The oxidizing species can be oxygen or water vapor, because we have discussed earlier that the oxidation can be done by two process. One is the dry oxidation, another is the wet oxidation, and in dry oxidation generally oxygen is used, and in wet oxidation water vapor or steam is used. So, in the view graph you can see that when we talk about the oxidizing species, basically this could be oxygen or water vapor depending on the oxidation is dry or wet, with surface concentration C0 molecules per centimeter cube. So, now next step is that what is the value of this C0? The value of this C0 for dry oxygen is 5.2 into 10 to the power 16 molecules per centimeter cube, and for wet oxidation its value is somehow higher, it is 3 into 10 to the power 19 molecules per centimeter cube. It is at 1000 degree centigrade and at a pressure of 1 atmosphere. Now, if you change the process condition, suppose if you increase or decrease the temperature, or if you increase or decrease the pressure, the values will be changed. So, this is the value of C0, which we have assumed that it is the concentration at the surface. Then what happens? Then the oxidizing species diffuses through the silicon dioxide layer, because remember here, since there is a oxide layer already formed on the semiconductor surface. So, now the oxidant or the oxidizing species must diffuse through the oxide layer to reach to the semiconductor surface, and once they reach at the semiconductor surface, they will react with the semiconductor for the formation of SiO2. So, the oxidizing species diffuses through the silicon dioxide layer, and thus there will be a concentration Cs at the surface of the silicon. This is the Cs at the surface of the silicon. So, this d is the thickness of the oxide already formed, and the oxidizing species must diffuse through the oxide species. Now, we have to calculate the flux at this F1, that means between the oxide and the oxidizing species, and also at this surface where it is between the oxide already formed and semiconductor. So, let us calculate the flux at F1 and F2. Now, if you calculate the flux at F1, that can be written as d dC by dx, which is equals to d C0 minus Cs by x. So, remember that this is the C0 and this is the Cs. So, C0 minus Cs by x is the concentration gradient, because dC dx is the concentration gradient, where d is the diffusion coefficient of the oxidizing species in silicon and x is the thickness of the oxide layer already present. At the silicon surface, the oxidizing species reacts chemically with silicon, assuming the rate of reaction is proportional to the concentration of the species at the silicon surface. The flux F2 is given by F2 equals to K into Cs. So, what we find that first this F1, which we can write as d of C0 minus Cs by x, and F2, which we can write as K into Cs. This Cs is the concentration at the surface of the silicon. This is the concentration at the surface of the silicon. Then what is K? K is a surface reaction rate constant for oxidation. At the steady state, this F1 and F2 will be equal, and at the steady state this F1 equals to F2 equals to F. So, now if you equate this equation, suppose it is A and it is B, and put the value of Cs in terms of F, then what we find that F becomes d C 0 by x plus d upon k. So, C 0 is the initial surface concentration of the oxidizing species, and d is the diffusion coefficient or diffusivity. So, the reaction of the oxidizing species with silicon forms silicon dioxide. Let C1 be the number of molecules of the oxidizing species in a unit volume of the oxide. Remember that this C1 we have assumed that it is the number of molecules of the oxidizing species in a unit volume of oxide. Then what will happen? Then we must be interested about the value of C1. So, there are 2.2 into 10 to the power 22 silicon molecules per centimeter cube in the oxide, and we add one oxygen molecule to each silicon dioxide molecule, whereas we add 2 water molecules to each silicon dioxide molecules. Because one oxygen molecule is oxygen is diatomic, so it is O2. Here in water molecule only one atom of oxygen is there. So, to make it oxygen molecule there must be 2 water molecules. So, this 2.2 into 10 to the power 22, this will be 4.4 into 10 to the power 22 centimeter cube if the oxidation takes place due to the water vapor. So, C1 value for dry oxygen and water vapor and for wet oxygen, it is different, it is twice because of the oxygen diatomicity. Then growth rate of the oxide layer, which is given by dx by dt, it is equals to F by C1, and that is equals to, if we put the values of F, then because F is equals to d into C 0 by x plus d by k, this is the value of F. So, if we put this F equals to F by C1, that is the growth rate, it is the growth rate dx dt of the oxide layer. So, if we put this F by C1 here, so what we get, that d C 0 by C1 by x plus d upon k. So, this is the growth rate of the oxide layer, and the initial boundary condition is that at t equals to 0, already there is an initial oxide thickness that we have shown here also. Already there is an initial oxide thickness, and this oxide thickness can be a result of earlier oxidation or pre-oxidation, or and in dry oxide condition we know that already there is an oxide layer forms at the surface of the silicon wafer. So, with this initial condition that d 0 is the initial oxide thickness, we can write that x square plus 2 d by k into x equals to 2 d C 0 by C 1 into t plus tau. So, this equation, and where tau is a time ordinate shift due to the initial oxide layer, that can be represented by the value d 0 square plus twice d small d 0 by k multiplied by C 1 by twice d C 0, and this equation can be written as x square plus a x plus b into t plus tau, where a is equals to twice d by k and b equals to twice d C 0 by C 1. Now, after time t, the oxide thickness can be written as x equals to d by k root over of 1 plus twice C 0 k square t plus tau by d C 1. So, it is the solution of this equation, where t is the oxidizing time, that can be small or large, because here it is very much important that when t is small one thing will happen, and when t is large the other thing will happen. So, throughout the time axis you can consider that the oxidation layer will not be uniform. For small t we shall see that it will varies linearly with time, and for large t we shall find that it will be parabolic. So, the rate constant will be different, and we shall analyze that thing. And for small t, because this is the reaction equation that x equals to, this is the reaction that x equals to d by k root over of 1 plus twice C 0 k square T plus tau by d C 1. So, now when t is small, for t is small, that can be approximated to x is equivalent to C 0 k by C 1 into t plus tau. How this can be approximated? That in that case we can consider that the numerator of the of this fraction, numerator of this fraction is very greater than 1, and we can write in this manner, and which is equals to b by a into t plus tau. This b by a is equals to C 0 k into by C 1, that can be written from here, that b by a, we have assumed that what is the value of a and what is the value of b, and if you take the ratio of b by a, you will find that we will arrive at this expression. So, at early stages of oxide growth, surface reaction is the rate limiting factor. At early stages of oxide growth, surface reaction is the rate limiting factor. The oxide thickness varies linearly with time, and this b by a is known as the linear rate constant. So, we shall arrive at two types of rate constants. One is the linear rate constant, and another is that we shall discuss now. It is for large t, when we shall find that this will vary as the parabolic nature. For larger t, x will be equals to twice d C 0 t plus tau by C 1, and in this case it will be x square equals to b t plus tau. So, as the oxide layer becomes thicker, the oxidant must diffuse through the oxide layer to react at the silicon dioxide interface, and the reaction becomes diffusion limited. The oxide growth then becomes proportional to the square root of the oxidizing time, which results in a parabolic growth rate. So, it is the equation of a parabola, x square equals to b t plus tau, and this b is known as the parabolic rate constant. And this is basically a rate constant, this is a kinetic thermal oxidation. So, that is a model, and we have seen that experimental data agree with the prediction through this model. So, now let us again consider the case of small t and large t to explain what is the linear rate constant and what is the parabolic rate constant. You see that at the onset of oxidation, when it is just starting, the oxidizing species reacts with the semiconducting material. So, if the semiconducting material is silicon and oxidizing species is oxygen, then oxygen reacts with silicon, and so that is a rate limited case. So, surface reaction is the rate limiting factor. So, it is the surface reaction, and the oxide thickness varies linearly with time. Now, when there will be an oxide layer already present, so what will happen? The oxidizing species must diffuse through the oxide layer to reach at the semiconductor surface, and in that case, as the oxidant must diffuse through the oxide layer to react at the silicon dioxide interface, and the reaction becomes diffusion limited, and then it becomes proportional to the square root of the oxidizing time. So, there are two rate constant, one is the linear rate constant, another is the parabolic rate constant. And for wet oxidation, this d 0 is very small and tau is almost equals to 0, and for dry oxidation, extrapolated value of d 0 at t equals to 0 is almost 20 nanometer. So, at the onset already we can assume that a 20 nanometer oxidation layer is formed on the surface of the semiconducting wafer for dry oxidation. Now, if we now consider the SiO2 structure, what is about the SiO2 structure? Here you see that a silicon atom is surrounded tetrahedrally by 4 oxygen atom. So, this is the silicon atom and it is surrounded tetrahedrally by 4 oxygen atom, one 2, 3 and 4 oxygen atoms, and the distance between the internuclear distance between the oxygen and silicon is 1.6 angstrom, and the internuclear distance between oxygen and oxygen is 2.27 angstrom. So, this is the structure, and these tetrahedra are joined together at their corners by oxygen bridges in a number of ways to form the various phases or structures of silicon dioxide. So, depending on how the oxygen bridges are formed, the silicon dioxide structures will be different, and one type of structure could be, say, the amorphous structure that we shall discuss. Another type of structure could be the crystalline structure or the quartz. In SiO2 sometimes you know that it is known as the silica, and silica can have two type of crystal structure. One is the crystalline nature, which is the quartz, and another is the amorphous structure that we shall discuss now. So, depending on the oxygen bridges, the crystalline or the amorphous structure is formed. Here you see that when this oxygen bridge is there and forms a ring, it is a ring like structure made up of 6 silicon atoms. This is one silicon atom, 1, 2, 3, 4, 5 and 6. So, 6 silicon atoms are there. If you consider here, there is also 6 silicon atoms. So, they formed a periodic structure, and this periodic structure, it has density of 2.65 gram per centimeter cube. Since it is periodic structure, we can say that it is crystalline in nature, and if these tetrahedra are joined together at their corners by oxygen bridges in this manner, then we can say that it is a quartz structure. This silica structure is a quartz structure. But if we consider that the structure is like this, that the tetrahedra are joined together at their corners by oxygen bridges in this manner, and here though there is a tendency to form the characteristics ring, here there is a characteristics ring with 6 silicon atoms. Here there is a tendency, but it is not periodic in the sense that sometimes it is more than 6, sometimes it is less than 6. There is a tendency to form the characteristics ring, but they could not make it. So, only 43% space is occupied by SiO2 molecules, and 57% space is not occupied by the SiO2 molecules. So, what happens that there are many spaces or void spaces available in this kind of a structure, and so predictably the density is 2.21 gram per centimeter cube, and if you compare this value of 2.21 gram per centimeter cube, you will find that in for crystalline structure is 2.65. So, here the structure is more closely packed than this type of a structure, and this is a amorphous structure because there is no periodicity, though there is a tendency. So, depending on the structure, there could be other type of structures also, and here the parabolic rate constant or the linear rate constant, we shall now see the variation of the temperature dependence or the temperature dependence of linear rate constant for two cases. One is when the wafer is 111 oriented or 100 oriented. So, we have considered that the silicon crystal can be two types of orientation. One is say silicon 100, another is silicon 111. So, both type of crystals orientation have been used for the growth of the oxides, and some interesting features we shall now discuss. So, this is the temperature dependence of the linear rate constant B by A for both dry and wet oxidation for 111 and 100 oriented silicon wafers. So, what we see? We see that in both the cases, that is for dry oxidation or for wet oxidation, the linear rate constant B by A, which has its units micrometer per hour, it varies as exponential, it varies as the rate constant is varies as exponential minus E A by k T. It is E A by k T. So, obviously, it is the activation energy, this E A is the activation energy, and that can be calculated from the Arrhenius plot, which is nothing but 1000 by T in the x axis and linear rate constant at the y axis. And we have calculated, and what is seen that the activation energy is 2 electron volt for dry oxidation. Here also for wet oxidation, activation energy is 2 electron volt, it is explicitly 2.05 electron volt, and the condition is at 10 to the power 5 Pascal pressure. So, we can see that the activation energy is equal in both the cases. So, that means these two lines are parallel, you can see. Now, this oxidation, this activation energy 2 electron volt, you can consider that to break a silicon-silicon bond, how much energy is required. To break a silicon-silicon bond, we can see that the energy required is 1.83 electron volt per molecules. So, if the silicon-silicon bond, to break it, the energy required is 1.83 electron volt per molecules. So, we can say that this closely matches with the value of the activation energy in case of both the dry and wet oxidation, which is 2 electron volt. And also we see that this B by A, that means the linear rate constant, depends on crystal orientation. It depends on crystal orientation in the sense that 100 silicon has value smaller than 111 silicon. So, why the value differs? Why it depends on the crystal orientation? So, that is very important observation which have been observed by the investigators for SiO2 thermal oxidation and to make. It is related to the rate of incorporation of oxygen atoms in silicon. It is related to the rate of incorporation of oxygen atoms into silicon, which in turn depends on surface bond structure of silicon atoms. So, how much oxygen atoms are incorporated into silicon, and that obviously depend on the surface bond structure of silicon atoms. Now, density of available bonds on 111 plane is higher than that of the 100 plane. So, linear rate constant for 111 silicon is larger, because available bonds, density of available bonds is higher, and obviously the rate constant will be higher in case of 111. So, we see that both for dry oxidation and wet oxidation, 111 silicon has higher value of linear rate constant compared to 100 silicon, because of the availability of the bonds, which is higher in number in case of 111 than that of 100. So, that is the characteristics of silicon 111 and 100. So, what we find that if you have a sample of say 111 silicon and 100 silicon, you have two samples suppose, and that two samples must have the linear rate constant different. For 111 the linear rate constant will be higher than the 100, because for 111 the number of available bonds is higher in case of the silicon. Then what about the parabolic rate constant? This was the temperature dependence of the linear rate constant, and this is the temperature dependence of the parabolic rate constant. Parabolic rate constant B, and quickly we can see that what is B? B is twice d C0 by C1. This d is the diffusivity or the diffusion constant. C1, what are C0 and C1? C1 is the value for dry oxidation, there is the number of molecules of the oxidizing species in a unit volume, and C0 is the oxidizing species at the surface. So, C0 and C1 we understand, and from that we can know what is B, the parabolic rate constant. The parabolic rate constant also its unit is micrometer square per hour. Here you see that it is micrometer per hour. So, obviously, the parabolic rate constant value will be different, and it is also varies as exponential minus E A by k T, where E A is the activation energy, and as usual if you have to calculate the activation energy in such process. So, what we should do, that we must take help of the Arrhenius plot. On the x axis you plot 1000 upon T, and the x axis and in the y axis you plot the rate constant, be it parabolic or linear, to calculate the activation energy. So, that is a standard technique, and here also we see that we have plotted 1000 by T in the x axis and parabolic rate constant and the y axis. This activation energy which was calculated from the Arrhenius plot is 1.24 for dry oxidation. For dry oxidation oxygen is used, and for wet oxidation water vapor or steam is used. In both the cases pressure maintained is 10 to the power 5 Pascal. So, activation energy in case of dry oxidation we find that it is 1.24 electron volt, and we can compare this 1.24 electron volt for the activation energy of oxygen diffusion in fused silica. In fused silica the value is 1.18 electron volt. So, the value quite matches well. Similarly, for wet oxidation the activation energy is found to be 0.71 electron volt, and this 0.71 electron volt, if we compare the value with the diffusion of water vapor in fused silica, we find that the value is 0.79. So, in both the cases diffusion through fused silica, whether it is by oxygen molecules or by the water vapor, depending on whether it is the dry oxidation or wet oxidation, we find that the activation energy values are quite matches well. However, one important difference between this parabolic rate constant and this linear rate constant is this. In linear rate constant we have seen that the crystal orientation has an effect, profound effect. However, for parabolic rate constant we find that it does not depend on crystal orientation. Why it does not depend on crystal orientation? Because it is related to the diffusion process through a random network layer of amorphous silica. So, since there is a random network layer of amorphous silica and it is the diffusion process, so it is a random process, and in random process the orientation dependence does not exist. So, what was the difference between the parabolic rate constant and linear rate constant? That the difference is the parabolic rate constant does not depend on crystal orientation. However, the linear rate constant depend on crystal orientation. Second important difference is that the activation energy for parabolic rate constant is different for wet oxidation and for dry oxidation. However, linear rate constant for wet oxidation and dry oxidation is same, it is almost 2 electron volt, and the activation energy for linear rate constant is higher than that of the wet oxidation. Activation energy for wet oxidation, you see that it is 2 electron volt, and here it is 1.24 electron volt and 0.71 electron volt. So, we can summarize these findings that the activation energy dependence, one is the linear rate constant, and number 2 is the parabolic rate constant. This parabolic rate constant does not depend on orientation. Linear rate constant, it depends on orientation. Then in linear rate constant, the value of activation energy E A is same for both dry and wet oxidation. Here E A is different for dry and wet oxidation. And the third difference, which is the value of E A, that E A, this value, it is higher than that of parabolic rate constant, and this is lower than the linear rate constant. It is 2 electron volt, here it is 1.24 electron volt and 0.71 electron volt. So, ultimately the activation energy, it is basically the process of diffusion, and for the parabolic rate constant, obviously it is the process of diffusion and through fused silica, either oxygen or water vapor, and in case of linear rate constant, it is the reaction at the silicon surface with the oxygen and the energy required to break the silicon bonds. So, the mechanism is different, it is well understood now. Now, some comments about the thermal oxidation, that the oxides grown in dry oxygen have the best electrical properties. More time is required to grow the same oxide thickness at a given temperature in dry oxygen than in water vapor. So, that means dry oxidation is very slow process, and if you want to grow say 50 nanometer or 20 nanometer oxide layer by dry oxygen, if the time required using dry oxidation is T1 and that using water vapor is T2, the same thickness, the thickness is 50 nanometer or say x nanometer, then we can say that for x nanometer to grow, either by x nanometer to grow either by I say dry oxidation or by wet oxidation, the time required is say T1 and T2, and obviously T1 must be greater than T2. So, more time is required to grow the same oxide thickness at a given temperature in dry oxygen than in water vapor, and thin oxide is grown by dry oxidation. Thin oxide means gate oxide in MOSFET, whose value is less than equals to 20 nanometer, or thicker oxides say field oxides in MOS integrated circuits, it is greater than 20 nanometer, for bipolar devices where the thicker oxides are required, oxidation in water vapor or steam is used. So, the limiting factor or the factor that must be chosen for growing the thin oxide or the thicker oxide is the thickness of the oxide layer. If it is less than 20 nanometer, one should go for the thin oxide, or if it is 20 nanometer greater than equals 20 nanometer, one should go for the thicker oxides, and thicker oxides are grown using water vapor. And now, here we have mentioned that gate oxide, field oxide, what are those? Let me very quickly refresh your memory that what is the gate oxide and what is the field oxide. If you see this diagram, you can find that this is the block diagram for a MOSFET, metal oxide semiconductor field effect transistor. It has grown using P silicon substrate. So, this is the field oxide. This is field oxide SiO2 and this is gate oxide. This is less than equals to 20 nanometer, this gate oxide. All are SiO2, but the field oxide thickness is greater than 20 nanometer. It is used for the isolation or the passivation, and this less than 20 nanometer it is for the gate oxide to make for the MOSFET. So, now with this idea we can say that for 20 nanometer we can use the dry oxidation process, and for greater than 20 nanometer we can use the thicker oxides, which is the result of the water vapor used. Now, it is the experimental results of silicon dioxide thickness as a function of reaction time and temperature for two substrate orientations. Two substrate orientations means one is 111, another is 100, because we have seen that crystal orientation has a profound effect on the oxidation. So, in these two view graphs we have shown you the oxide thickness, which is in micrometer, as a function of oxidation time, as a reaction time, and temperature also. You see that in this graph it is for dry oxidation and it is for wet oxidation, and here the temperature used is 700 degree centigrade to 1200 degree centigrade. So, both for the low and high temperature oxidation here used. Low temperature means say 700 to 900, and high temperature is almost 1000 to 1200 degree centigrade. These dotted curves or is for the 111 orientation crystal or substrate, and 100 is the solid curve. Here the same thing here at 3 different temperatures it has been shown. One is 900, another is 1050 degree centigrade, and third one is 1250 degree centigrade. Remember that here also the dotted curves are for the 111 substrate and solid curve is for 100 crystal orientation of the substrate. This is when the growth of the SiO2 has taken place in steam or water vapor, and this is the growth of the oxidation oxide layers in dry oxygen. So, now what we find? We find that oxide thickness grown on 111 substrate is larger than the dotted curves. These are the 111. It is larger than that grown on 100 substrate, because of the larger linear rate constant of the 111 orientation that we have discussed earlier also, that because the density of the bonds is higher in case of 111 orientation, then here the growth rate is higher, linear rate constant is higher, and so the oxide thickness grown is also higher. And oxide films grown by wet oxidation method has thickness 5 to 10 times thicker than that by dry oxidation at any temperature, say 900 degree centigrade. Suppose this is the curve for 900 degree centigrade, the solid one is for 100 and oxidation time is on the x axis. So, let us take the value at 1 hour. What is the thickness for 900 degree centigrade growth? We see that it is 0.01. So, it is less than 0.02 somehow here. So, it is less than 0.02 micron 1 hour. Here for 1 hour it is greater than 0.2 micron. This is 0.1. So, it is 0.2 and even it is greater than 0.2 micron. So, it is less than 0.02 micron, less than 0.02 micron in case of the dry oxidation, and whereas it is greater than 0.2 micron for wet oxidation. So, we can say that it is 5 to 10 times thicker than that by dry oxidation. However, this thick layer is electrically not the best one. Dry oxygen oxides grown in dry oxygen have the best electrical properties. Another important thing from this studies is that thin oxide to grow precise control, and to make the precise control over thickness, slow growth rate is important. Slow growth rate is important where one can precisely control the thickness, because one can see that in process technology, when we talk about the oxidation, that this is the oxidation, it is one of the process steps by planar technology, and we can see that oxidation is the first one with lithography, ion implantation, metallization, etc. And this oxidation step, very good quality gate oxide is required, otherwise what will happen, the leakage current will increase like anything, and because the leakage current will increase and the interface states will be more in case of the leakage. So, gate oxide must have good electrical property, and this electrical property can be achieved if we use the oxide grown by the dry oxygen method. So, that is important consideration in case of the oxidation. This is a thermal oxidation, because we shall come across other oxidations also, like the CVD of silicon, or say for other types of oxidation, we shall find that there are other applications also, not that it is only used for making the gate oxide, in some cases for the isolation, for some cases to making the mask for the diffusion or lithographic pattern, and thick oxide layers are grown, and in that case obviously we will not use the dry oxidation, rather we shall go for the wet oxidation or the oxidation by the CVD technique or other techniques that we shall discuss in later stages. So, control is very important, precise control is important, and then the growth rate must be slow enough. Then what are the processes, what are the major steps that people have taken or the industry have taken? So, the formalities are, one is the growth in dry oxygen at atmospheric pressure and lower temperatures. Lower temperatures means 800-900 degree centigrade. So, here you see that it is 800-900 degree centigrade, atmospheric pressure and low temperature. This is dry. Another protocol can be growth at pressure lower than atmospheric pressure. So, then it becomes more slow, atmospheric pressure and lower than atmospheric pressure, it can be more slow, the rate will be less. Growth in a reduced partial pressures of oxygen by using a diluent inert gas. The inert gas can be nitrogen, argon or helium together with gas containing the oxidizing species. So, that means we can reduce the partial pressure. How to reduce the partial pressure? We can use some inert gas to dilute it, and that inert gas can be this argon, nitrogen or helium. Then if it is grown by reduced partial pressure, then obviously the growth rate will be very slow. And another process that can be used is the use of composite oxide films with the gate oxide films consisting of a layer of thermally grown SiO2 and a overlayer of CVD SiO2. So, that means you can use composite oxide films with the gate oxide films consisting of a layer of thermally grown SiO2 and a overlayer of CVD SiO2 means silicon dioxide made by chemical vapor deposition. So, these are the processes that can use. There are many other processes also people have reported, but mostly the industry adopted this one, that is the growth in dry oxygen at atmospheric pressure and lower temperature. So, mainstream approach for gate oxide is that one can use the vertical oxidation furnaces. I have shown you the oxidation furnaces. This is the oxidation furnace that we have discussed earlier. It is a horizontal type of thing, and you see that here on the silicon wafers are placed on the fused quartz board. A large number of silicon wafers you can use. Then there is a resistance heater, or the heater can be other types of, say it is a lamp glow, or it can be microwave. So, any kind of heating can be accomplished, mainly the resistance heater is used, and there is the oxygen or H2O plus carrier gas, the carrier gas can be high purity nitrogen or argon, which will transport the oxygen or the water vapor to the silicon wafers or the furnace region, where the actual reaction and the diffusion will take place. And obviously, there will be vent, the unreacted gases or that will build up, that will be vented out from this quartz tube reactor, and then there will be exhaust. So, this is the standard protocol that we have used, and obviously, we have discussed that this must be accompanied by the clean room. This must be accompanied by the clean room, because without clean room one cannot make this oxidation very good. Otherwise, there will be a large number of dust particles that will have its own imprint or signature on the other surfaces or on the wafer surfaces in the later stage. So, what we see that this oxides which are grown at the furnace, that furnace can be a vertical one. Vertical oxidation furnace can grow reproducible high quality 10 nanometer oxides to within 0.1 nanometer across the wafer. So, if you have a wafer say of 6 inch and the growth can be, oxide layers can be of say 10 nanometer plus minus 0.1 nanometer, plus minus 0.1 nanometer. So, that is very precise, and this 10 nanometer is nothing but where we have seen that it can be, it is used in case of the gate oxide in MOS technology, and also the growth at atmospheric pressure and at lower temperatures. So, that is the mainstream approach for gate oxide, which has been done in case of the industry. So, now we see that vertical furnace is the most efficient furnace, and it is horizontal one, and where at atmospheric pressure, normal atmospheric pressure, that means 76 centimeter of 76 millimeter of mercury, and also that low temperature means 800-900 degree centigrade, so that it becomes a slow process, the thermal shock is not there, and at one go a large number of silicon wafers can be made to oxidized. So, these are the advantages, and so the vertical furnace has its own efficiency. So, now till now what we have discussed, that in oxidation, the oxidation can be a dry one. This is a dry one, and you see that first there is a silicon dioxide interface, and that moves into silicon during oxidation. First silicon dioxide interface and it moves. So, more and more silicon is consumed for the formation of SiO2, and one example that you can try to solve, if a silicon dioxide layer of thickness x is grown by thermal oxidation, what is the thickness of silicon being consumed? So, if it is x, then how much thermal oxidation and will be the silicon dioxide? If a silicon dioxide layer of thickness s is grown by thermal oxidation, what is the thickness of silicon being consumed? And given the molecular weight of silicon is 28.9 gram per mole and the density of silicon is 2.33 gram per centimeter cube, the corresponding values for SiO2 are 60.08 gram per mole and 2.21 gram per centimeter cube. So, you can try this example to see what happens for and you will find that this silicon dioxide interface moves into the silicon during oxidation and more silicon is consumed. This is a very interesting thing, and once the SiO2 is grown, then the oxidizing species must diffuse through the grown SiO2 to reach at the surface, that means at the interface between the Si and SiO2 to make it reacting with the silicon atoms for for the growth of SiO2. So, now we can summarize our lecture in the sense that in this way, that the oxidation can be two types. One is the dry oxidation, another is the wet oxidation. Then dry oxidation, we have seen that oxygen gas is used, whether for wet oxidation H2O vapor, that means water vapor or steam is used. And we have seen that this dry oxidation, it is the thickness is less value of T is less. For wet oxidation, it is greater than the T for the dry with the same condition. And also we have seen that the kinetics of growth is that first a layer of SiO2 is formed on the silicon, and this silicon SiO2 layer moves. So, what happens, the first it is the rate limiting factor that affects the reaction of the Si with oxygen to form the SiO2, that is the linear in nature, and the rate constant depends on linearly. And then the oxidizing species diffuses through the SiO2 layer to reach the surface for the reaction. So, it can be the parabolic rate constant. So, depending on that those model, one is this, that linear rate constant is there, and it is different from the parabolic rate constant after the initial oxidation. This is after initial oxygen or oxidation, initial oxidation, because it is diffusion takes place through this initial layer of the oxidation. So, linear rate constant, we have seen that it is very much depend on the orientation of the crystal, that we have discussed, that the linear rate constant, it depends on orientation, parabolic rate constant does not depend on orientation. Then the linear rate constant, the activation energy is same for both dry and wet oxidation. For parabolic rate constant, that activation energy is different for dry and wet oxidation, and also the value of the linear rate constant activation energy for the linear rate constant, it is 2 electron volt, it is higher. Why it is higher? Because this is the amount of energy required to break the silicon bond. Here it is for the diffusion only. Then we have come across the different kinds of structures of the SiO2. One can be of quartz type of structure, another can be of say silicon, one is quartz type of structure, another is amorphous type of structure, and we have seen that the density of the quartz structure is greater with closely with its packing fraction is very high. And why it is so? It is because it has a periodic nature, and the silicon atoms form a ring of 6 atoms, and it is perfectly crystal, it is perfectly periodic in nature. And for our quartz, for amorphous type of crystal structure of SiO2, we have seen that it is more, or the density is very less. Why? Because only less than 50% space is used by the SiO2 molecules, and so the impurity, particularly the sodium or that type of impurity, can diffuse through the SiO2. That thing must be taken care of. Then we have talked about a mathematical problem which is given by this that silicon layer thickness to grow, SiO2 layer thickness x is to grow, how much silicon is being consumed. So, with this we end the discussion on the oxidation, that is we have discussed that it is one of the most important and gate oxide under which a constant conducting channel can be formed between source and drain. Then field oxide, it is provides isolation from other devices, and these two oxides are formed mainly by the thermal oxide. Next day we shall discuss the dielectric layers or other polycrystalline silicon and metal film. Thank you.